So here I want to do a curve sketching using the ideas of 351 with a rational function. That way we can talk about vertical and horizontal asymptotes and how to approach that. So we've got a function 2x plus 1 divided by x minus 3. And so the first thing I want to do is I want to find the domain. With a rational, to find the domain, we set the denominator equal to 0 and solve for x, and those are all the values we can't have. So x minus 3 equals 0. If I solve for x, that means that x cannot be 3. So as long as we avoid x equal to 3, then we should be okay for this since we cannot divide by 0. So the domain of f is all real numbers going up to 3. I skip over 3 and I go from 3 to infinity. Okay, now I want to find the critical values. When I take the derivative, I set it equal to 0 or where it does not exist. Since this is a rational, it's got to be used, I guess you could use a couple different rules, but the easiest one is just to use a quotient rule potentially. So let's just use the quotient rule here, and I'm going to do low d high. So low is x minus 3 times d high, so the derivative of the top is 2, and then minus high, the high is 2x plus 1, minus d low, derivative of x minus 3 is just 1, all over low or low squared, so I take the bottom and I square it. If I multiply this through, I'm going to get 2x minus 6, and then I also have a negative 2x here, so those x's cancel, but then this negative multiplies in, and so I end up with negative 7. Okay, negative 7 in the numerator. If you combine like terms here, the denominator stays the same, x minus 3 quantity squared. Now, when I look at this derivative right here, I look and I say, okay, the only way a derivative can equal to 0 for a fraction is if the numerator is 0. Well, when can negative 7 equal 0? This can never happen. That's a contradiction. So I know that f prime of x cannot equal 0. However, f prime of x can be undefined. And how do we make it undefined? When we take a number and we divide by 0. That's undefined. So if I set the denominator equal to 0, x minus 3 squared equals 0, square root both sides, x minus 3 equals plus or minus 0. That tells me that x equals 3 is a value that does not exist. Therefore, x equal to 3 is a critical value. So I know one of my critical values is 3. Okay, what about double prime? What happens here? So once again, I have a rational. So I'm going to do low d high minus high d low all over low low. And so low d high, the derivative of the numerator is 0, minus high. So minus and minus makes a plus 7 here. And then d low, I'm going to have to use a chain rule since it's something raised to the 2. So I'm going to bring the 2 out front and then subtract 1 from the exponent and then multiply by the derivative of the inside. Derivative of the inside is 1. And so now I've got a big old mess in the numerator. In the denominator, I take that and I just square it. Okay? So the numerator cleans up a little bit. How does this clean up? Well, I have this term goes away because when I multiply by 0, that's just going to cancel everything out. So I need negative and negative make a positive times 2 times 1. That's positive 14x. I'm sorry, 14. And so now I see a 1 factor of x minus 3 and 4 factors of x minus 3. So one of those factors cancels, and so that's why we're left with just 14 in the numerator and 1 less x minus 3 in the denominator there. Now, same thing here. This is the second derivative. 14 can never equal 0, so it's impossible for f double prime to equal 0. However, you can have 14 divided by 0 as long as I plug in x equal to 3, right? And so if I plug in x equal to 3, then that point doesn't exist. Now, vertical asymptotes. Okay, vertical asymptote. If I go back here, I saw that x minus 3 was a vertical asymptote because it's not in the domain of this rational here, and it's not a whole. We can't factor it out. If you take the limit as x goes to 3 from the right of 2x plus 1 over x minus 3, this is going to get me 6, 7 over a positive 0, which means that is positive infinity. So that tells me right there, that's the work I want to see, that that's a vertical asymptote. Okay, so it's a left-handed or right-handed limit for that one. Okay. You could have done the left-handed limit if you wanted to. To me, I like doing right-handed limits. I'm right-handed. So my brain thinks a little easier when I pick numbers a little bit bigger. All right. Now, for a horizontal asymptote, I'm going to take the limit at infinity. So limits at infinity, I push this out. The numerator and the denominator degree are equal. Therefore, I'm just dividing the coefficients. You think back to college algebra. If you take this limit here, you're going to get 2. Okay? Work out that reciprocal thing. I don't know if you remember this, but if I had a limit as x goes to infinity of 2x plus 1 over x minus 3, I multiply by the reciprocal of the highest powers, and so this becomes limit as x goes to infinity of 2 plus 1 over x divided by 1 minus 3 over x. And this term and this term both limit to 0 as x goes to infinity. So I get 2 plus 0 over 1 plus 0, or minus 0 technically, and that gets me 2 as well. Okay, so that's actually the proper way to do it without a shortcut there. Take the limit there, get that. Now, I find since my limit at infinity is 2 for both ways, then it only has to be just at 1 at least. But the good thing about having them both the same here is that means I only have one horizontal asymptote. If I had maybe that was a -2 there, then I would also have a y equal -2 for a horizontal asymptote. But that's not the case. It's just 2 for both of them. Okay? So now what I want to do is I want to create a number line, and I want to determine the subintervals and where we're increasing, decreasing, and then next number line I want to do for concave up, concave down. When we did the first derivative, we only had one critical value. So we've got one mark here. So I've got this interval split up to -infinity this way and +infinity that way. So let's work through it. I'm just going to pick 2 points. I pick 0 and I pick 4. No magic to the numbers, just one to the left, one to the right. In the middle, we know that the point x equal 3 does not exist. It's not defined for our function. So it cannot be a relative max or min. However, if I evaluate at 0 here, my derivative, I plug in 0 to this function right here, get 0 minus 3 in the denominator. It doesn't really matter what it is because when I square it, it becomes positive. So the numerator is negative, the denominator is positive, so that gives me an overall negative number, which tells me that I am going to be decreasing on that interval. Now at f prime of 4, if I plug a 4 in here, once again it doesn't matter because the squared is going to make it positive. The numerator is always negative, so I end up taking a negative divided by a positive, which produces a negative. And once again, I'm decreasing. So it's like I'm decreasing, and then something weird happens, and then I'm decreasing. So I'm basically decreasing for all real numbers except x equal to 3, which is not even in our domain. So there's no maximum, there's no relative maximum, and also there's no relative minimum. Because if you think about it, you're a function that's going down all the time, and then you take a break, and then you still go down. There's nowhere where this is like the top or the bottom, because you just no change in direction from increasing, decreasing. Okay. Now, second derivative test, or the second derivative itself, 14 over x minus 3 quantity cubed. Okay, this one only has a critical value where it does not exist, again, at 3. So I'm going to pick a point to the left and to the right. I'm just going to pick 0 here, and I pick 10 just to be different from the 4 here. No real reason. So if I plug in 0 into my second derivative, well, the numerator is positive. The denominator, though, is cubed, okay? So if I plug in 0 here, 0 minus 3, that's negative. A negative number cubed is still negative. So I have positive divided by a negative, which gets me a negative. So I'm actually decreasing here. Okay, I'm sorry. I'm concave down like a cup. Okay, I'm sorry, concave down like a frown. All right, so, oh man, I'm just having some fun here. Okay, so 10, if I plug in f double prime of 10, then what's going to happen? Well, if I plug in a 10 here, that's going to get me a positive number. Cubed is a positive number, and a positive number in the numerator. Positive, positive, positives make a positive. And so this is greater than 0. Therefore, I'm concave up like a cup. Over here, concave down like a frown. Got it. All right. Now, the problem here, the reason this isn't a point of inflection is because what do we know about that point? It does not exist for our function. It's a vertical asymptote. And so then there's no point of inflection. There's no relative max. There's no relative min. So you could have that as a scenario there. Okay, very possible. So now what we want to do is we want to evaluate the function at all the critical points. Well, I just told you, you cannot plug in 3 for any of these. So therefore, we have no critical relative max or mins or point of inflections, but we can find some x and y intercepts. So let's do that. Let's get the x-intercept and the y-intercept. How do I get the x-intercept? I set y equal to 0. The only way a fraction is equal to 0 if the numerator is equal to 0. And so I set 2x plus 1 equal to 0. If I solve for x here, minus 1 divided by 2 gets me negative 1/2. And so I get this point right here. That's an x-intercept. It's a location, not x equals something. That's a vertical asymptote, so make sure you put a location. And then y-intercept here, this is setting x equal to 0. So everywhere I see an x, I put a 0. So I plug a 0 in for all my x values. So I get basically 1 divided by negative 3. I don't know why I have that there, but that should be a 1. And then that's going to get me negative. Oh, shoot. Okay. I need to fix that. So that's going to be a negative 1/3 technically. All right. So whenever just to make sure I got the function right. Okay, when I plug a 0 in here, yeah, that's going to knock out those, and it's just going to be negative 1/3. Okay? So this is technically negative 1/3, not negative 1. So just keep that in mind as you're watching this video, because it's going to keep saying negative 1. So that's negative 1/3 technically. Okay? So let's graph all of the points that we know. Right? I know I have a vertical asymptote. I'm going to label it VA x equal 3. HA horizontal asymptote at y equal to 2. And so this cross here is kind of going to be our guideline for how our rational looks. And so you kind of know, look, we're decreasing everywhere, right? So I know that I'm going to be going down, and then I'm going to be going down. What changes is the concavity. Not only are we decreasing this way, but we're concave down over here. And not only are we decreasing this way, but we're concave up over there. Okay? So since we're decreasing, I have negatives. And since we are concave down, I have negatives on this side. Now, my intercepts, I have an x-intercept of -1/2. My y-intercept is negative. Technically, it's -1/3. So keep that in mind. I drew my picture a little wrong, so it should look more like that. Sorry about that. Okay. And then on this side, how did we know it was up there? Well, look, guys, if you're having trouble, you just plug in a point. But look, we know that this is decreasing. That's what those negatives tell me. On the bottom side, put decreasing or increasing plus or minuses. On the top side, put your concavity. The concavity, positive, like a cup, okay? Up like a cup, all right? And a point here, if I plug in 5, so if I plugged in f of 5, it's going to output 11/2. So I just picked a number there, nothing special about 5. But like if it had told me it was like, if I plugged in 5 and it was it was like down here, then that would tell me I was down on this side, right? So plugging in a number helps you figure out kind of where your bearings are for your curve. And I just plugged in x = 6 here into my original function there. Okay? All right, so once again, this should be 1/3, -1/3, and then we can change this here. And so now that looks pretty good. Okay, let me look at this. I'm just too much. This is gonna bug me. All right. All right, so there you go. So now it kind of looks more like it should. Okay? Cool. Let me zoom out so you can kind of see the whole problem in one shot. All right, guys.